Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for extracting minimum element from the stack. Let's look at the problem description. We have to design a stack that supports push, pop, top and retrieving the minimum element in that stack in constant time. Let's take a look at the example 1. So basically they give a series of operations and the input for those operations in two arrays. First is the min stack operation, initialize the stack, and the push with value -2, push that element into the stack, and push the second element 0 and third -3, and then get min. So when we call this get min, at that time -3 is the smallest element. Next operation is pop. So that pops the -3 out of the stack, and then top function returns the top element which is 0, and the get min function return the minimum number present in the stack. In this case -2. Even though -2 is deep inside the stack, we should have a function that retrieves that in constant time and return it. So constraints for this problem are the value is ranging from -2 to the power -2 to the power 31 to 2 to the power 31 -1. And the pop, top, get min operations will be done only on a non-empty stacks. So so the number of calls to these function is at most 30,000. Let's look at the approach to solve this problem. So we are given a series of operations and the corresponding input, and this is an expected output. Okay, and we have to implement a function which returns the minimum number present in the stack in order of 1 time complexity. Okay, so in a regular stack, if you want to access the element present deep inside the stack, we have to pop all the elements above that minimum number. Only then we can access this minimum number, right? But we wanted to return this in order of 1 without removing this element. For that, we need to keep track of the index of the minimum number present in the stack. Whenever we add an element to the stack, we have to update that index. Okay, that is at a stack level. And one more information also we need to maintain. Basically, for each element, when we add, what was the previous minimum number present in that stack. Basically, whenever we add an element, we have to remember the previous minimum numbers index. Okay, for example, when we pop out the current minimum number which is present in the top, when we remove that, the index should point to the next minimum number present in the stack. So we always have to remember what was the previous minimum index whenever we add an element. Okay, so with these two information, we should be able to return the minimum number present in the stack in order of 1 time. Okay, so that's what I have listed here. So we can solve this problem by keeping track of the minimum element at the stack level and also with respect to the top element. Okay, so first we have to define the element of the stack. So basically each entry in the stack has two values. One is the input value and the other one is the index of the previous minimum number. And then we define a stack with a slice of that element whatever we defined, and then we keep track of the current number of elements in the stack and then the index of the current minimum element present in the stack. So this is the stack level minimum index information. Okay, so whenever we push an element, first we initialize the new element with the input number and the current minimum index, and then we check whether the stack is empty. If it is empty, then the minimum index is the element we are pushing. Okay, so we set that to 0. If the stack is not empty, then we have to check whether the element being pushed is smaller than the current minimum number present in the stack. In that case, we have to update the minimum index of the stack and we have to increment the count. So by doing that, we always keep track of the index of the minimum number in the stack. Okay. And when we do pop operation, we have to update the minimum index of the stack with the previous minimum index value present in the top element. Okay. And we remove the top element from the stack. Next, the top operation is simply return the top element of the stack, and get min operation return the value of an element present at min index in the stack. Let's look at the flowchart. The input for this procedure is stack and the value. First we have to create an element to be pushed. Basically we have to pair the input value and the previous min index and push that structure into the stack. Okay, so the current minimum index of the stack will be assigned to the previous min index of the element. Okay, so once this is created, we check whether the stack is empty. If so, then the current element being pushed is the smallest element in the stack. So we simply set the minimum index to 0. Otherwise, we check whether the input value is smaller than the current minimum element in the stack. If so, we have to update the stack's minimum index with the current element's index. Okay. Otherwise, we do not have to update the minimum index. And finally, we add the element to the stack and increment the count. So the flowchart for the pop operation, the input is stack. When we pop an element, we have to update the minimum index of the stack with the previous minimum index value of the top element. Okay, and then we remove the element from the stack and we decrement the stack count. The top operation simply return the top element, and the get min operation, the input for this procedure is stack, and this operation return the value present at stack min index. Let's move on to coding. First I define the element structure, which has two members. One is value of type int and the other one is the previous minimum index of type int. Next I define the min stack structure, which it has an element called stack of type slice of elements, and then the count to track the number of elements in the stack, and the min index to track the index of minimum number in the stack. Next I write the constructor function. It creates the min stack with empty slice of element and the current count to 0 and the current minimum index to -1. Next I write the push function. First I create the element structure with the past input value and the current stack min index. Then I check whether the stack is empty or not. If it is not empty, then I read the current minimum index in the stack and read that value. If the current minimum index is greater than the incoming value, then update the minimum index with the current count. So the current count value is an index of the incoming element. If the stack is empty, then I set the minimum index of the stack to 0 because this is the first element. So the minimum index value will be set to 0. Then at the end I append the element into the stack. Next I write the pop function. So in this function I update the minimum index of the stack with the top element's previous min index value. And then delete the last element in the slice. And decrement the count. Next I write the top function. This will simply return the value present in the index count minus 1. And getMin function return the value present in the minimum index. And here I forgot to increment the count. Next I'm going to run the test cases. All the tests passed. Next I'm going to submit this program. Cool, this program is accepted. Next I'm going to do the code walkthrough with sample input. Let's do the code walkthrough for this input. So the expected output is this. Okay. So the first operation is min stack. Basically this will call the constructor function which initialize the stack with empty slice of element, and the current number of elements in the stack is set to 0 and minimum index is set to -1. That's what we are seeing here. Okay. Next push operation is called with -2. Okay. So you see, first we initialize the element structure with the value and the current minimum index which is -1. Okay, basically this is the previous minimum index of this element. So when we remove this element, this value is the one going to be restored as the next minimum element in the stack. Okay, so once this structure is initialized, then we check whether the stack is not empty by checking the count. In this case it is empty, so we simply initialize the minimum index to 0. Okay, and append that element to the stack and increment the count. So when we enter the iteration 1, the stack is empty, total number of count is 0, previous min index is -1. When we leave, -2 is pushed into the stack and the previous minimum index for this element is -1, and the total number of elements in the stack is 1. The index of the minimum number present in the stack is 0, that is the first element. The element at index 0 is the min index. So the next push operation is called with input 0. Okay, so in this case again we initialize the element structure, but the stack is not empty. So in this case we get the current minimum index of the stack and check whether that value is greater than the current value being pushed, which is 0. But in this case it is not. So we are not updating the minimum index. And then we append the element to this stack and increment the count. So when we enter this iteration, there is only one element in the stack. So the count is 1 and the minimum index is 0. When second element is pushed, so 0 is added and the previous minimum index is at 0. So that's why the second parameter is 0 and the total number of element in the stack is set to 2 and this value is the index at which the minimum number is present, so which is 0. So this is the minimum number, so its index 0 is set in the minimum index value. So next push operation is called with -3. So in this case we first initialize the element structure and check whether the stack is not empty. It is not, so the stack is not empty. So we check whether the current minimum number -2 is greater than the value being pushed, which is -3. So that is true. So we have to update the minimum index of the stack to the current count, which is 2. So that is equal to the index of the element being pushed. Okay. So we update the minimum index to 2 and then we add the element -3 and then increment the count. So that's why we see there are 3 elements and the total number of elements in the stack is 3 and we have updated the index of the minimum number in the stack to 2 because this is the minimum number. So that index is set to 2. Next, the getMin function is called. So the getMin function read the value present at min index. So current min index is 2. So it read this value and return it in order of 1 time. Next operation is pop. So when we pop -3, so whenever we do pop, the previous min index of the element being popped out will be assigned to the stack min index variable. So in this case, the previous min index is 0. So when we enter this function, it is 2, but after the pop operation, it is set to 0. Okay, because the current element being popped out has its previous min index 0. So we restore that value. Okay, and then we decrement the count. So that is so it changed from 3 to 2 and remove that element from the stack. So next operation is top. It will simply read the element present at index count -1. So we return 0. The last operation is getMin. So in this case, we read the number present at index 0, which is -2. Next, I'm going to do the time and space complexity analysis for this solution. Let's do the time complexity analysis for this input. As we have seen already, all these 4 functions are executing in order of 1 time. So all these functions are directly using an index to read the data and append an element on top of the stack in constant time. And with respect to the space complexities, it is order of n because we need to allocate space for the previous min index in each element. Okay, so in this case we pushed 3 elements, so we need additional space for the previous min index value. So if there are n elements pushed, we need n space. So the space complexity is order of n. Thanks for watching this video. Have a great day.